All right. Yeah, no, no. Once you answer a question, you go to the next one. So you are done with that question. All right, sure. All right. Any other questions? Anyone? All right. So on Wednesday, we have our lab. Of course, we have our activity this Wednesday, and next Monday, our midterm exam. It would be, again, 10 questions and 2 points each. And it is on Canvas, start at 10 and possibly about 1 hour or so, but you will see the time on Canvas. Then make sure that your internet works, because I cannot do anything. Absolutely, I cannot do anything. I want you to make sure that internet works, Canvas works, computer problems. I cannot, this is your part to make sure these items work. Otherwise, you can take the test on campus, actually. You can use the computers, go to campus and take the test over there. All right. With this now, I think if you have questions, you can ask me. Otherwise, let's move on to continue with beams. Tell me, what do you remember about beams? Don't look at the notes or your book or so. Tell me, what do you remember about our discussion on beams? I want 3 items that you remember. Anything. What did we discuss? What do you remember?
There are 2 types of beams.
All right, very good. We talked about 2 types of beams. Anyone can say what are these 2 types?
Timoshenko.
And another one?
Euler.
Euler-Bernoulli, very good. Yes, these are 2 different types of beams. And the Euler-Bernoulli includes the effect of, only the effect of bending. It doesn't include the effect of shear, but Timoshenko includes the effect of deformation due to both bending and also shear. Anything else? You tell me one more item before we move on.
Reason why the Euler-Bernoulli it's only considered bending is because the length is a lot longer than its width. Therefore, the shear is very small. Forgot what the number was.
Yes, yes. When beams are long, effect of shear is less than when a beam is short. So when length of a beam considered compared to its height, if the length is, let's say, 10 times its height, the effect of shear is just 3% of the deflection. So we can neglect it. But if it is shorter, then if it is 8 times the height, then the effect of shear is actually 5%. But the shorter it gets, the effect of shear is more pronounced. So we tend to use the Timoshenko theory that includes the effect of shear. We said that there are three examples are just simply supported beam here, cantilevered beam, and also overhanging beam. These are these 2 types of beams. This was the notation. We said that 2 degrees of freedom per node, force in the y direction and moment. These are the loadings, 2 degrees of freedom displacement in the y direction, and also rotation, phi1, at each node. So 2 degrees of freedom per node, and the element has 4 degrees of freedom. Therefore, our element stiffness matrix, we found this. These are the shape functions we discussed. And also we found the element stiffness matrix, very important. Always we want this one, element stiffness matrix. Once we have this, then we are fine. We can use this for, by direct stiffness method, create the global one, and then solve for displacements. And then once we have the displacements, then everything else post-processing, we can find them. So today, let's solve an example problem. We didn't solve an example problem. So our plan today, look at one example problem, then we talk about Timoshenko theory, look at the element stiffness matrix by Timoshenko, then we talk about when there are distributed loads on the structures on beams. And we solve an example problem when there are distributed loads. And that concludes our discussion for today. Let's start with this one example on beams. This is a beam fixed here, loaded at this end, and it is supported on a spring. You know the spring stiffness, modulus of elasticity, and moment of inertia. The question is to find the displacements and rotations at the nodes. It's node 1, node 2, node 3. Forces in each element, reactions, and draw a shear bending moment diagram. To solve this problem, tell me, how many different types of elements do we have in this problem? And what are they?
We have a beam and a spring.
Very good. There are two types of elements here. One is the beam element, spring element. So we need two types of element stiffness matrices. For the beam element, we already know. So this is our model, two elements, element 1, element 2, beam element, spring element. This is the beam element. According to Euler-Bernoulli, we derived this. I showed you the highlighted. This is this one, EI over L cube. This is element for the beam. And this is for the spring. This is the first type of element. It's the simplest one. We learned it before. At the beginning, we learned about spring element. This is K, 1 minus 1 minus 1, 1. These are the degrees of freedom here. This is V1, Phi1, V2, Phi2. I need to create the global stiffness matrix. Tell me, what is the size of the global stiffness matrix? Anyone? What is the size of the global stiffness matrix? We have a beam element which has two nodes. So 2 degrees of freedom per node. So it makes it 4 by 4 for the beam element. And for this one, it adds just, this is a spring element from node 2 to 3, but this is the common node. So this adds just 1 degree of freedom. That would be displacement V3. So the global stiffness matrix should be 5 by 5. And that is this one. Just by superposition or by direct stiffness method, we know how to create this one. Dump everything in the right spot. This is here V1, V1, V2, V2. This is element 1 sits here. Element 1 sits here. And element 2, it is V2, V3, V2, V3. So this one sits here, 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 and here. And pay attention, there is a factor out here. So, but this factor is actually part of this matrix. We have just factored this out. So, but this is EI over L cube. So if you multiply it, we see that just 1K remains. So this is the spring element that actually sits here. But do not ignore this EI over L cube. Do not forget this. Do not overlook this. This is a part of this matrix. So applying the boundary conditions fixed at this node. So displacement and rotation out and displacement out here. So this is V1, Phi1, row and column out, V3, row and column out. So we end up with two equations, two unknowns. This is these two, just plug the numbers to EI over L cube. First of all, modulus of elasticity, I, length, and these parameters here, 12 plus K times L cube divided by EI. Just plug the numbers here. times V2 phi2 here. This is V2 phi2. It is F2y M2 force at node 2. We have this negative 4,000, and there is no moment, external moment here. So there is no external moment, but this is the force. We solve for V2 and phi2. This is the Nastran's job, finishes here. It returns the results back to PMAP for post-processing. V2 and phi2, remember phi2 is in radians, so pay attention, the unit also in radians. That's it. The rest is now like what we have done before. The next question was to find the forces in each element. Okay, well, forces in each element, this is for the beam element, use this one. Forces in each element. Let me show you the formula for this one. This is this one. According to Euler-Bernoulli, this is the force vector, element stiffness matrix, and this is the displacement vector. We already know this displacement. We know the element stiffness matrix. Then we can solve for forces and moments in each element like this. So this is this part. Forces in each element. For the beam element, this is this one. This is K times displacement vector. It goes from node 1 to node 2. Displacement and rotation, these are here, these two. These are the forces and moments. We've multiplied. This is not solving. It is just we have multiplied this matrix by this matrix. So this is post-processing forces and moments in node in element 1. These are this spring element. The second element is spring element. We can just use the F3 is negative kV2, plug the numbers. 1,772 pounds is force which is upward also at node 3. So this force is positive upward. These are the forces in these elements. Next question was to find what? Reactions. We already know these reactions here and here. So this reaction at node 1, we found forces in element 1 here. This is in the beam element, we found this one. So this is a force F1y, 2,230 pounds, according to our sign convention, positive upward. So this is the force upward, and moment is positive counterclockwise, according to our sign conventions in finite element methods. So this is positive, it is counterclockwise. These are actually the reaction forces, and also this one. In general, to find the reaction forces, we use the global formula. The general procedure is this actually, to use the global formula multiplied by the displacement vector. We already know all of them now. After we solve for this displacement, we know the displacement, we know this, then we can solve for reaction forces. But in this case, we can see that reaction forces are simply F1y is this reaction force, this one 2,230, and moment, we already found it here. This is the moment. Is at node 1, which is attached to the wall. It's coming from the wall, coming from the reaction force, and at node 3, it is 1,772 upward. And drawing shear bending moment diagram, it's from statics, from solid mechanics. This is element 1, node 2. These are the reaction forces, external force, and the reaction force. So shear bending moment diagram, if it cut it at any section here, this force would be is upward, so it would be downward here, which is positive according to our sign convention to plot shear bending moment diagram. And moment here is this is counterclockwise. According to our sign convention in solid mechanics, it is negative. And it is 0 here. So it varies linearly from negative 534 and goes to 0 here. So this is the moment diagram, and this is the shear diagram. All right. Any questions on this problem? No questions on this. So let's move on to the next discussion is about Timoshenko. Timoshenko, we said that includes the effect of shear. This is what you see here. This is this beam. Now, according to Euler, we neglect the effect of shear. We just include the effect of moment, but the effect of this moment, it means that these planes perpendicular to the axis of this beam remain plane like this. So for example, here it remains plane here. It remains plane here. But the reality is not. The reality is actually what you see here. It warps here. This warping is because of shear, because the effect of shear. This shear force produces a shear stress here, which is 0. Shear stress here is 0. So you see this element didn't distort. If you consider a square here, this remains a square. This is also 0 here. If you consider a stress element here, it remains a square here. Shear stress was 0. It didn't distort it, but shear stress is maximum here. If you consider a rectangular element before loading, it is distorted now like this, like a parallelogram. In other words, the effect of shear is to warp this like this. This is what it was neglected in Euler-Bernoulli. It was not included. Here we want to include this. Here is what this is the differential length of this beam. Blue one, blue color, Euler-Bernoulli. Red, Timoshenko. You see the effect of warping here. You see the warping. Euler-Bernoulli didn't. It is straight. So now if you look at these angles, if you draw a horizontal and perpendicular to this blue one, which is the Euler-Bernoulli, this is due to bending. Now, if you look at this red one, if you draw a perpendicular, if you draw a tangent to this and perpendicular to this, then you see there is another angle here, which was neglected by Euler. This angle is due to bending. This angle is due to shear. Total rotation is adding them together, this plus this. So this red one is deflection due to M and V, but this blue one is Euler, it's just due to M. Total rotation is dV over dx. dV is displacement in the y direction. So dV over dx is actually total rotation. It is phi of x, this one, plus beta of x, this one. Due to bending, due to shear. Add them together, it's a total one. Now, we can show that phi is given by this formula, not going into very details to derive this actually, but phi is given by this formula, and V displacement is given by this. Now, this phi that you see here, there is one term here, this G. This takes care of the effect of this shear that we neglected it by Euler theorem. This is the extra term that we need to incorporate to find the angle of rotation, taking into account the effect of shear. Now, what is this G? Well, this G is given by this. It is EI KSAG. This KSA, this area of the cross section. KS is a factor. KS is a factor that modifies this area. KSA is called shear area. Now, this KS is a factor depending on what type of cross section we have. If it is rectangular cross section, if it is 5 over, it's 5/6. If it is circular cross section, it is 0.5, 0.9. Or if it is like thin members like this, it is 2. Now, using these two equations, like what we did for Euler-Bernoulli, it's not something really new totally. It's just Euler-Bernoulli. Just for rotation, we use this angle, this equation. So applying boundary conditions, we need to find A1, A2, A3, A4. These coefficients, you see here, this A1, A2, A3, A4 here, A3, A2. We need these coefficients, apply boundary conditions, the same as what we were doing before. Displacement at node 1 when x is 0. Just put x0, we get A4, and this is V1. When x is 0, rotation is, it is this one. This is, rotation is this. When x is 0, this would be out. So it would be A3 plus 6A1G. This is this one. It is Phi1. Do the same thing for node 2. When x is L, V is V2, and this is the equation when for rotation, when x is L. For equations for unknowns, we get this one for V. That is our new V. You see G is taking care of the effect of shear. Compare this V to this V according to Euler. You see previously we found this one, and that is V here according to Euler. So you see there is no G here, a simpler version compared to this one. This V. Effect of G rotation. Do the same as what we did for Euler for finding using the formulas from strength of materials. Moment is EI, second derivative of V with respect to X, and V, shear force, is EI, third derivative of V with respect to X. This is our V. Second derivative with respect to X gives moment. Third derivative of this with respect to X gives shear force. Like what we did for Euler-Bernoulli, we end up we create these 4 equations in matrix form. This is this one, F1y m1, F2y m2, like Euler-Bernoulli. It is now this one multiplied by displacement vector. This is called our element stiffness matrix according to Timoshenko. Now, if you look at this, I want you 30 seconds. Look at this. This is element stiffness matrix according to Timoshenko. Compare it to element stiffness matrix according to Euler. Tell me what is the difference. Look at them, tell me what is the difference.
It has G in it.
You're right. It's actually the same as the previous one, except just you see 12G, negative 12G, negative 12G, 12G. It is actually the same as what we had highlighted here, this one. Except you have 12G, negative 12G, negative 12G, 12G. So this is this one, but it has another term here that takes care of the effect of shear. So this is more complete solution, more accurate solution. But if G is 0, it reduces to Euler. Put G 0 here, then it reduces to Euler. It is like a complex number. Complex numbers are more advanced compared to real numbers. Real numbers, we don't have imaginary parts. But if complex numbers have imaginary parts, if imaginary part is 0, then it reduces to the real numbers. So complex numbers are more advanced. The same as this one. If G is 0, it reduces to Euler formula. There is another form of writing this actually. So we can write this introducing a new term phi. If we define this phi like this, which is 12G over L squared, then this element stiffness matrix, we can write it in this form. This phi, by the way, is dimensionless. Is it? Yes, this is the non-dimensional shear correction term phi. So this term is actually dimensionless. You see EI, it would be pound inch squared. Then this would be, this is pound per inch squared multiplied by inch squared, pound times inch squared. This is also a coefficient, so it's nothing. So this is a dimensionless quantity. So if we introduce this new term here, then the equation reduces to this. This is another form of this one. So either one that we want to use is fine. It doesn't matter. So that is the new K that we use to solve beam problems if the length of this compared to its height is small. If it is less than 8, usually we tend to use this one. But again, this is a rule of thumb. You can always use this formula. It doesn't matter. It is more accurate if you include this one. All right, that was our discussion about Timoshenko. Any questions on this Timoshenko beam theory?
It seems pretty intuitive.
Very good. All right, so we are ready to move on then. So let's now talk about one more item and solve an example after that. That would be our discussion for today. Beams subjected to distributed loading. Remember, when load is distributed on this element like this element 1, node 1, node 2, load is distributed here. Finite element methods doesn't like this behavior. We can't work on this. We have to convert it to this form. Put these forces, some equivalent nodal equivalent forces at nodes, a force F1y and a moment M1 at this node. The same at node 2, a concentrated force, F2y, and a moment, M2, at this node. This is how we can handle this. Our formulas are written for nodes. So this is the way we want. But real world gives us this. This is the real world situation. We have to convert it to this. That's our discussion today. The question is, what is this F1y? This is the displacement corresponding to associated with this force, then there is a displacement. Associated with this moment, there is a rotation. But this is what we want, F1y M1, F2y M2. These are called equivalent nodal forces. Equivalent nodal forces is equivalent to this, but at nodes. So how do we do this? Well, we use the work equivalence method. Work equivalence method means that work done by this force on this beam, it is the same as forces and moments done by these concentrated loads on this beam. In other words, work is the same. We put work here equal to this one, we get what we want. We want this one, this one, this one, and this one. So work of distributed is the same as work of discrete. Work of this distributed is simply this force times Vx dx. Vx is this displacement in the y direction. Wx is this one, it is force per unit length. This is this one times differential length, it is force times displacement gives work. This is work due to the distributed load. Now, work due to the discrete, well, it is simply, let me finish this piece first. Work due to distributed load. This is this one. We found it before. We can use Euler-Bernoulli, make it a little bit simpler. This is Euler-Bernoulli. We found V. It is here. This is this V. Use this V. Here, this is our V here. This is this one. So this is W, whatever loading you have times V, which is this one according to Euler-Bernoulli, and then put it here to find W, work due to the distributed load. Now, work due to the discrete load, work is always force times displacement. At node 1, at node 2, due to force, due to moment, moment times rotation. At node 1, moment times rotation at node 2. Put them equal to each other. So this is work distributed loading, work concentrated loading at nodes. Now, in order to proceed, we need an example to see what type of loading, for example. It depends on what loading we have to find the equivalent nodal forces here. What loading is it so we can proceed? Let's look at an example problem. This is this one. Uniformly distributed load. Load is uniform on this beam. The question is, what are these equivalent nodal forces? Remember, we said F1y, F2y, M1, M2. These are called equivalent nodal forces. This is this. We want to find this. We want to find this moment. We want to find this force and this moment here. Work equivalence theorem, it says that work of the distributed loading is the same as work of the concentrated loading. This is this one. Plug the numbers. In this problem, our loading is uniform. So it is negative W. It is negative W. This is our V. This is the V times dx. It is equal to, this is work due to what happened? I think I touched this one. Let me go back to these two are equal to each other. This example, this is V, this is V, this is work due to the concentrated nodal forces. If we put the coefficients of V1, V2, Phi1, Phi2 from the left side of the equation to the right side, we get this one. F1y, remember this is our unknown. It is the same as F2y, it is the same as this one, it is negative WL over 2. M1 is this and M2 is this. These are the unknowns. It means that this distributed loading that we have, it is equivalent to this one. At node 1, F1, Y is negative, so it's downward. It is WL over 2 downward. This is this one. Moment, remember counterclockwise was positive, so this is negative. It is clockwise. WL squared over 12. The same as node, at node 2, it is positive, so it is counterclockwise. And at node 2, there is WL over 2 downward. This is what we want. These are called equivalent nodal forces. Okay, once we have this one, just one more note here before finishing. Our global formula now for this type of problems, which we have equivalent nodal forces, it would be this one. F is equal to KD. Now we add another this forces FO. FO is called equivalent nodal forces. In this formula that, in this problem that we solve, equivalent nodal forces is this one. It's negative WL over 2. These are this. In matrix form, it is this. And for an element, lowercase here, remember this is global, capital. This is for one element, F is KD minus FO, lowercase. We use this formula to find the local nodal forces or moments. Now, this one was for this example problem that we solved. So, but we have different types of loadings. We have linearly varying, we have parabolic, we have different types of loading. So what should we do? Each time we don't want to go through this integration. So in our textbook, there is Appendix D that gives equivalent nodal forces for various type of loadings. So let me show you this Appendix D. Let me share the, let me see, you see the textbook I'm showing here, I think. Let me go to Appendix D. This is Appendix D. This is Appendix D of our textbook. It gives you what? It gives us the, it gives equivalent nodal forces, Appendix D, for various types of loadings, whether we have, for example, this is concentrated force at the here, or we have two different loadings, uniformly distributed loading, this is partially, this is triangular, and whatever shape we have, this continues here, Appendix D of our textbook, it is here, it gives you various types of loadings and their corresponding F1y, M1, F2y, M2. And this is the finite element model that we use. Remember, this is one element, length L. This is F1y, upward positive, moment, counterclockwise positive. The same for node 2, force and moment. Different types of loadings, and then you can find F1y, M1, and F2y here, M2. These are the equivalent nodal forces for different types of loading. This case that I showed you, this example that we went through, can you tell me which case it is here? Which case?
Case 4.
Case 4, very good. Yeah, this was the one that we looked at. You see, remember we got WL over 2 and negative WL squared over 12, and F2y was also negative WL over 2 and WL squared over 12. So these are different types of loadings. If you continue here, let me see if I can show you more. This one here, again, it continues under the next page. It shows also a couple of more for this one, and also when it is parabolic or when there is a concentrated moment here. For this case, it is just a concentrated moment here. So we can read the concentrated forces and moments. All right, so Appendix D of our textbook gives you this one. Let me go back to let's go back to our notes here. I have it here also, this Appendix D I included here. This is for different loadings it shows, and different cases. For example, this case 4 that we had uniformly distributed loading. These are the equivalent nodal forces, and a couple of other cases. That is all I wanted to discuss. The next and the last discussion we have today is just to look at an example problem. Otherwise, we are done with everything we wanted to discuss on beams on chapter 4. Any questions? All right, no questions. So let's look at this example problem. This is a beam, distributed loading. We don't want like this. We cannot handle this unless we convert it inside. Remember, FEMAP showed you when you applied distributed load on the beam. Remember 2 weeks ago or so, you solved the beam problem and you had distributed load. FEMAP shows you this distributed load, but inside actually FEMAP converts this distributed force into concentrated equivalent nodal forces and moments at nodes. So look at this example problem. Node 1, 2, 3, fixed here, pinned. This is linearly varying loading. intensity 4,000 pound per feet. These are cross-section and material properties are given. The question is find the nodal displacement and slopes. Forces in each element. And the reaction forces. In order to do this, we have two elements here. This is our model here. We have two elements, 1, 2, and let's use Euler-Bernoulli beam theory. This is 10 feet, so this is long beam. In this problem, element stiffness matrix for element 1 is the same as for element 2. It is EI over L cube. These are the degrees of freedom for element 1. It is V1, P1, V2, P2. For element 2, it is V2, P2, V3, P3. This is this one. We need to create a global stiffness matrix. Can you tell me what is the size of the global stiffness matrix?
Six by 6.
Why 6 by 6? You're right. Very good. Why 6 by 6? Anyone?
We have 3 nodes with 2 degrees of freedom each.
Very good. 3 nodes, 2 degrees of freedom per node. That gives 6 by 6. So this is the global stiffness matrix, capital K. It is 6 by 6, V1, P1, V2, P2, V3, P3. The same here. This is 6 by 6 by direct stiffness method or by superposition. This is this one. Applying boundary conditions. Can you tell me how many boundary conditions do we have here? How many boundary conditions here? Displacement 0 in the y direction, rotation 0, displacement 0. So from these 6 equations, 6 unknowns, how many should I delete? These are homogeneous boundary conditions. They are 0. If it is 0, remove them from the system of equations. So what should I remove here?
V1, V1, and V2.
Very good. You're right. V1, V1, and V2. These are out. That's what you see here. V1, V1, V2 out. Row and column associated with these, all these 3 out. So we end up with actually these 3, which is V2, V3, V3. There is a rotation here, V2 and V3, V3. That is the global stiffness matrix. Now, the new item that we learned today was this one. Very important, equivalent nodal forces, because here we have distributed load on this structure. We cannot handle it like this unless we convert these things into equivalent forces at nodes. Now, what are they? Appendix D will help us. That is what I want you to practice. Each one of these items, you have to be comfortable with this using Appendix D. Now, let's do it one by one. I do a couple of them with you and then leave the rest for you. Now, node 1, it's attached to the wall. So there is a force from the wall. So this you see F1y. It is from the wall. Now, there is a distributed load. Look at element 1 only. This is element 1. There is a linearly varying load, triangular. It is a vertex of this triangle. Go to Appendix D here, let's see. This is the rectangular loading. This is case 5 here. But the point is that our vertex is on the left, but this vertex of this triangle is on the right. That's okay, it doesn't cause much problems. This is the vertex here. This force at this node, it is negative 3WL over 20. So I have to add this one for the vertex at that node 1. Okay, so negative 3WL over 20. Go back. This is this one, negative 3WL over 20. There isn't anything else for force at node 1. Let's go for moment. Moment at node 1. It is also the constraint from the reaction is also moment here. There would be M1 because of the wall. Now, because of this distributed load, there is an equivalent nodal moment here also. At the vertex of this triangle, remember this vertex is on the left, this vertex is on the right. Equivalent moment here at the vertex here, it is this, WL squared over 30. But this is, if this vertex was on the right, it is positive. But on the other side, it is negative. So I have to just change the sign of this one if it goes to the other side to make it negative. So it would be negative WL squared over 30. All right, so this comes here. Negative WL squared over 30 is this one. All right, so that takes care of element 1 now. Element 2 consists of F2y. There is a reaction now. Look at node 2. Node 2, there is a reaction from the support F2y. Now, F2y, which is this one, by the way. Now, we have a case here. Node 2 is connecting this element 1 and 2. So some effect comes from element 1, some effect comes from element 2. So it is in between 2. So we have to consider. One is from this side, element 1, and from element 2, it is a trapezoidal loading. So we can convert it into 2 simpler loadings, a uniformly distributed load and a triangular load. So 2 cases for element 2. But let's look at element 1. I want you to tell me for element 1, this is the, it's not the vertex here. This is the, I want the force at node 2 from this. What should I do here? This is this one. What is the equivalent nodal force here?
The -7 WL20.
Very good. Very good. This is, remember, we are talking about this side of this, which is -7 WL over 20. So put it here. This is this one, -7 WL over 20. This is from element 1. That takes care of the effect of element 1. Now element 2. Element 2 has now this trapezoidal loading, which consists of a rectangular and a triangular. So like this one, I think I added this figure here. This helps. This is what element 2. So this trapezoidal, we can divide it into 2 simpler geometries. Now for this one, it is simply what? It is, we did it, uniformly distributed load. It is WL over 2. We did it. This is this one. So it's negative WL over 2. Let me see. It is this one. Negative WL over 2. This is from the uniformly distributed load, from this rectangular. Now we have another one, this triangle, vertex of the triangle, vertex of the triangle here. This force negative 3WL over 20. This one is because of this negative 3WL over 20, and that comes here. That concludes the force at node 2. Let me do one more item, then I leave the rest for you to do it everything one by one yourself. At node 2 now, there is a moment also here, but there is no reaction from the moment here. Like here, we had M1 here, but there is no moment from the support. So
Bless you.
thank you. There is no moment from the support here, so we need to just go for one moment from the distributed load here and 2 moments from this uniformly distributed load and triangular. So 3 moment terms we need. Let's go one by one. First of all, from element 1 here, moment here. That would be this moment, which is negative WL squared over 20. But remember, this was on the other side. So this is negative here, but the other side it is positive. So I have to change the sign of this. It would be WL squared over 20. Okay, WL squared over 20 is for the moment WL squared over 20. This is this one. This is this one from element 1, from this side now. Now let's go to this side. 1 rectangular, 1 triangular. This one, it is actually, we did the WL squared over 12. Remember, we did this one. WL squared over 12 is when we solved it, but this one is on the, let me show you. This is this one. This one, so this is from this side. So this was, now this is uniformly distributed. This is on this side, left side, WL squared over 12 negative. So this is this one that we did before, also WL squared over 12. And finally, there is one moment because of the vertex of this vertex here. One moment term we need vertex of this one, but remember it was on the other side. So the moment here is WL squared over 30, but we have to change the sign of this to make it, bring it to the other side. So negative WL squared over 30, and that goes here.
Professor,
All right.
is this
Yes.
part of F2y or is this a different variable?
Oh, no, it's not a part of F2y. This is moment. This is this here is moment. You see here is F1y, M1. Our formula. Let me go. You see, in general, the formula that we have, we said that. Let me. You see, our formulas are like this: F1y M1, F2y M2. So these are this is force moment at node 1, force moment at node 2. So this is our combination. The same here. This first term, this is force moment. Force at node 1, moment at node 1. Force at node 2, moment at node 2. Force at node 3, moment at node 3. So this is not continuation of this. If you see that the units are not even the same. Look at this. This is 3/20. This is WL. What is it? This is force per unit length times length. It is force. This is force. What is the units for this? WL squared. It is multiplied by another L. It is force times length. It is moment. So these terms that you see, these are moments. This moment at node 2. This is force at node 2. This is moment at node 2. This is force at node 3. And this is moment at node 3. All right.
Okay, thank you. Yeah, I was just a little confused because they weren't labeled.
Yeah, so like this, now we are ready to move on. That's it. And then the rest just apply boundary condition, these 3 out. So these 3, plug the numbers here. Our force, including the equivalent nodal forces, it is here. Just plug in the numbers, we get this. Remember W here, it is 2,000. It is not 4,000 because total it was 4,000. But when we divide it into half like this, a rectangle and a triangle, so it would be 2,000. So our W is 2,000 in this formula that we use. And length is 10, so plug the numbers. This is our force vector, including the equivalent nodal forces. That's it. It's 3 equations, 3 unknowns, these 3 and these 3. So this setup is like this. E, other velocity, I, L cube. Remember, it is 10 feet. I convert here everything to pound and feet. It is easier to convert it. I put it a note here. Convert it to feet here. Pay attention. That is pound per inch squared times inch to power 4 makes it pound times inch to power 2. Pound times inch squared. Divide by 12 squared makes it in feet, and this is also feet. And plug the values here. We have this force vector. Solving, this is Nastran's job is finished here. This is the rotation and displacement at nodes 2 and 3. Remember, phi is in radians. And this length we calculated, of course, everything here was in feet. So it is in feet, but then converted into inches like this. That's it. Nastran's job is finished. The rest is post-processing. The question was to find what? This part, forces in each element. To find forces in each element, just use the forces in each element. It is this one. F is equal to KD minus FO. FO is the equivalent nodal forces. Element 1, this is this one. K times D, displacement vector for element 1. Remember this for element 1. Force vector for element 1. Multiplying, we get this. These are the forces and moments in element 1. Similarly for element 2, this is force vector. K times D, displacement vector, is equal to this minus FO, equivalent nodal forces. This is for element 2 only. Remember, this is for element 2. So this is just this part of this, we have everything here. So for element 2, we just take the pieces from element 2. So this piece, because this was coming from element 1. So this would be this piece. This was coming from element 1, this piece. So 2 terms here, 2 terms here. And so this is what you see here for element 2. These 2 pieces, 2, 2, and 2. Multiplying, we get forces and moments in element 2. And the reaction forces always go with the global formula, with the very general formula that we start with. F is KD minus FO. This is global displacement vector. Remember, this was 6 by 6 matrix. Displacement vector that we already know, FO, this is this one. This is this that we, this, everything here. We are solving now for reaction forces. These are the reaction forces here. So going back to, for the reaction forces, we have, this is this one now. This is F1Y, M1, and M2, and F2Y. These are the reaction forces. These are that we can solve for these 3 items. These 3 items are just for checking, actually, because we don't have anything, just the left side should be equal to the right-hand side. So this is just for checking that we have done it correctly. These are done, this here shows as a note here, equivalent nodal forces. For the everything here, it is this one, negative 3,000. This is negative, it is downward. Moment, negative, it is clockwise. It is this value. At node 2, a force of 20,000 downward, this one. Moment, clockwise. Force downward, 17,000 downward, negative. And a moment counterclockwise, positive. So these are the equivalent nodal forces for the complete structure for the beam. And then here, going back to this one, this is F1Y, M1, and F2Y. We find these are the reaction forces, F1Y, M1, and F2Y. Others are just for checking. It checks that this is the same as the other. All right. I have one more item to do. Just nothing new, just an extra information. Any questions about this problem so far? All right. Then I have one piece here just showing each element. Therefore, element 1 experiences the following loads. I just want to show. This is element 1, 10 feet long, node 1, node 2. This is distributed load. Suppose somebody asked us if equilibrium is satisfied or not. So just go for element 1. Free body diagram of element 1. This is the loading at node 1 now. Let's go back. For element 1, we found this negative 20,000, 20,500 pounds downward, and this moment should be clockwise. This is negative clockwise. So put these two here. 20,500 downward, and this is the moment clockwise, negative it was. And at node 2, remember, this is just whatever belongs to element 1. Don't look at element 2, just everything from element 1. 30,500, force downward. And this is the moment clockwise. This is negative. 30,500, positive. And then this is the moment negative. Do the same thing for element 2 also. For element 2, the loading was trapezoidal. There was nothing here at node 3. This is for element 2. This is for element 2. We found these items. 30,000 force upward, and this is the moment counterclockwise. Force upward and counterclockwise, that's the moment, and that's it. It must be in equilibrium. The same, this must be in equilibrium. Is it in equilibrium or not? Sum of forces in the y direction. Quickly check for me. True or not? Sum of forces in the y direction. Check it for me, 1 minute. All right. Satisfied or not?
Yeah, it's satisfied.
30,000 pounds upward. Now, if you, this is 4,000, so this is 2,000. 2,000 and 4,000 is 6,000. Half of 6,000 is 3,000. 3,000 multiplied by length of this 10 feet. So 30,000 down, 30,000 up. So yes, and some of moments you can check that this is correct. All right, this is just for checking whether equilibrium is satisfied or not. That's all I wanted to discuss about our discussion on beams. We are done with beams. The next discussion that we will have later, of course, it would be on frames. But any questions about beams, what we discussed today? Or anything that we discussed so far? Because on Monday next week, we have our midterm exam again. Any questions so far? Everything that we have discussed. Chapters 1, 2, 3, and 4 would be on the test.
We don't have to be on Zoom for the midterm.
No, there is no need to come to Zoom. You can directly go to Canvas. Make sure that your Canvas works. Make sure your internet works. If there is any problem, I cannot do anything. It is just a test on Canvas for about maybe 1 hour or so. You go to Canvas. If you are not sure about your computer at home, you can go and take the test at school. Go to campus, use any of the computers in the computer lab or anywhere in the library or so, if you can, wherever you feel comfortable, or to a friend's house or whatever, but make sure that your computer works. Go to Canvas, start at 10 o'clock and possibly about 1 hour or so. You will see the timing. I have not made the test yet, possibly around 1 hour maybe. You answer 10 questions, enter a number or multiple choice or true or false, 10 questions. You do not go back. So whatever numbers you enter, make sure that you are happy with that number you enter and it is finished. You cannot go back. That's your answer. That would be your answer. Each question 2 points also. After that, there is no class. So we will meet the week after that for our lecture. All right, any questions, anything else? All right, everyone, I stop here. Of course, if you have questions always during my office hours, you can stop by. Otherwise, have a good rest of the day. I will see you on Wednesday for our activity. We are going to solve a 3-dimensional solid mechanics problem. We should be good at this stage with FEMAP. So for more rigorous analysis, we do 3D analysis that we are going to start from Wednesday this week. All right, see you all on Wednesday. Take care, everyone. Bye.
Professor.
Thank you.
Thank you.
So right now it's 1 hour.
The test,
Yeah.
About 1 hour. I do not know exactly. I have not made the test yet. As I said, I do not know, possibly around 1 hour, but you will see the time on the test. It shows you, Canvas shows you the remaining time or how long you have. It should be about 1 hour, but you will see the exact time on Canvas.
Okay, thanks.
All right, sure.